So let's change our difficulty level. What's the volume of this cone? Okay, and I'm going to go to here. We're going to go to 0, 0. What's your favorite Z?
1.
Good answer, Mark. 2. Does it matter?
It's the height.
Not in particular, right? That's just the height of this cone. And this cone's special, right, because it has one specified value, right? Okay, so how would I set up an integral for this thing's volume?
Gonna be a triple.
It has a
Integral of z.
2. It
How's-
would be negative 2.
I pointed positive Z down.
Oh, okay.
Don't get attached to the usual coordinates. Just put them wherever they're convenient.
Would we want to do
not
little slices, like circle slices?
Yeah, we could do little circle slices, right? You guys see that? So, I want to set up a triple integral. Yeah? And
X,
what's the
Y.
function I should be integrating?
Do you do dr deflated dz?
I don't know.
Doing that wrong.
Oh,
So what function should I be integrating to find a volume?
1.
That
1.
or
If I was doing a double integral, right, then I'd want to integrate the function.
Okay.
You guys see that? Okay, so I'm going to integrate 1. What variable, order, choice,
Well,
coordinate system?
Gotta have an R in there.
Okay, I probably want to do radii, right?
Yeah.
You guys see that? So do I want cylindrical or spherical?
Cylindrical.
Cylindrical, right? Because I don't have a top on my ice cream cone. So I want to do D,
Something.
so I should do R, D, R, D, theta, D, Z. And I'm up for rearrangement on this, right? Okay, so,
DZ being last is nice because we have a set number to number
maybe.
for initial glance.
Okay, so where do your radii go?
I had to find
We're doing R's first, right?
z and
R square thing.
So, right, this is for a specified height and specified angle. What's your radius look like?
Root 2?
So your radius for a specified height and angle looks something like this, yeah?
Yeah.
Okay, so it goes from 0.
Yeah.
I'll do that one. You guys sort the other one out.
Square root of x squared plus y squared.
2.
So that's
Would be,
But that's in Cartesian, right?
yeah.
yeah.
So what's this function
Square root
z in polar?
square root of r
Square root of
cosine
r
theta squared plus r sine theta squared.
Okay, r squared cosine squared theta plus r squared sine squared theta. So you get
1. No, R.
R?
R squared times. Yeah.
right. You factor in r squared out. You use your trig identity.
You get lines.
Then you got the square root of r squared gives you r, right? Okay, so your radii go from 0 to
R. Like
0 to z.
2.
perfect 0 to z, right? You guys see that? So your radius goes from nothing up to z as r, right?
Oh,
And I have to put the r, right? That's the thing I'm trying to get rid of in terms of the other variables.
because this is z equals square root of x squared plus y squared. It's a 45-degree angle. cone.
Yeah.
Or else
Okay.
we'd just be plugging the r.
You guys see that? The cone that I've specified, right, is the one where the phi is 45 degrees. You guys see that? Okay, so I went from 0 to z in the r's. How about thetas?
0 to 45, right? Or
Pi over
pi
Pi over
2
2?
to pi over 2. Negative. No, not negative. 0 to pi
That'd be
over
0 to
4.
pi over 4. Or 0 to pi over 2.
That's
Okay,
0.
so where are your thetas? Where do they live?
Oh, it would be 2 pi.
They're horizontal, right? So if I sliced through this thing,
Oh.
right, for a specified z, I already got rid of the r's, right? So for a specified z, what happens to the angle? Well, it starts here at the x-axis, right?
Yeah. Goes around.
Goes all the way
And then it goes all the way around.
2 pi.
Yeah.
So that reads like 0 to 2 pi to me.
I think theta is always going to be our easiest one. Generally.
It depends. Yeah, usually the angles are pretty easy to eyeball, and it's the heights or something
So
that'll
this
cause
like
you
move
headache.
towards you, it's like not in the y. Would it be like just 0 to pi?
So if the
Like
wait,
it's above the x-axis. Would it be 0 to pi, or it's not centered?
oh, so like if I had this thing sliced in half or something.
Yeah.
So if I had it sliced in half, I'd want to go from minus pi to pi, right?
Okay.
You guys see that? You want to, yeah, you want to spend a little time and play with this, but certainly there are other options, right? So don't get attached to the 0 to 2 pi, right? That would mean it goes all the way around in the horizontal direction. Okay, how about the z's? Where your z's vary from?
0 to 2.
0 to 2. Perfect. You guys see that?
So they don't have to be in terms of the others.
Nope, they don't have to be in terms of the others. Sometimes they are, right? Like, certainly this one, my theta values, right? Those could have what's in them? Do they have r's in them?
No, they could have Z's.
No, they can't have r's, right? Because you already got rid of that. But they could have z's. You guys see that? So that radius, right, could be a function of z. Like if I had a cone that was missing a big chunk. You guys see that? Alright, so I got this. What do I do with this? Integrate? Okay, so I got the integral from 0 to 2, the integral from 0 to 2 pi of r squared over 2, evaluated from
Z.
0 to z, d theta dz.
So
So it's
R squared from Z squared over 2.
Okay, so I've got the integral from 0 to 2, the integral from 0 to 2 pi of z squared over 2 d theta dz. You guys want to see a cool trick?
Sure.
That's times 1, right?
Yes.
This crap, z squared over 2, that's a constant, right?
Yeah.
So I can pull it through the integral up to here.
Just ignore it for now.
You guys see that?
You can only
Yeah,
pull
okay,
one
yeah.
layer though, right?
Yeah,
So
but
it
I can
doesn't
only
have-
pull it one layer, right? Because the other layer is z's, and it's
And we're
not
not-
constant
Yeah,
there.
we're not integrating so Z's yet. You can only pull it through the layers that it's constant.
Yeah, so I can get the integral from 0 to 2 of z squared over 2 times, and now I'm going to put in the parentheses that Mark was asking about the other day. So I got 0 to 2 pi, the integral of 1 d theta, right? dz. What's this crap?
Well,
Does that have any z's in it?
No.
Yeah.
No.
So it's just 2 pi. Yeah, it's 2
Yeah, it's just 2 pi, but does it have any z's in it?
No, because you can't plug it in.
No, there's no z's in it, right?
Yeah.
So I could pull it out, because it's constant.
Just play with it.
You guys see that? Yeah, I just want to show you a trick, which is if you have a product of two functions, right? One that depends on z and the other one that depends on theta, you can really kind of pull it apart into two integrals and multiply them. You guys see that? So here, yeah, out of the blue guy, right, the d thetas, I'm going to get 2 pi. So I'm going to end up with 2 pi times the integral from 0 to 2 of
Z squared over
z squared over 2 d
2. Z.
z. Okay,
Z cubed over 6.
so you get z cubed over 6. So I've got 2 pi z cubed over 6 evaluated from 0 to 2 gives you 2 pi times 8 over 6.
4 over
you 4/3 pi.
Wait,
What?
no.
No. 8 pi over
See, that's why you stopped there.
8 pi over 3. Yeah.
Gives you 8 pi over 3, clearly. Perfect. Good? Questions, things?
On the part we put z equals square root of r squared, how'd you get all that stuff?
That was me looking at
Trig sub.
this thing and thinking, okay, in polar, x is r cosine theta, and y is r sine theta.
Oh, okay, got it.
And then I just made a substitution.
Okay.
I said theta and wrote phi. I meant theta. Cool? So you just make this substitution and then fiddle with it. It's a little bit like trig sub, right? Except what?
No triangle time.
Yeah, in trig sub, right, you have to go back to the variable you were talking about. Why don't I have to go back here? Like I turned x's and y's into r's and thetas.
Because we
We're
just
working in
use
cylindrical.
cylindrical.
Yeah, I was really working in cylindrical and I was trying to calculate a number anyway.
Yeah.
You guys
We
see
went
that?
from what we didn't want to what we wanted.
Yeah.
Instead of going out of what we wanted to get back in.
You guys cool with that?